All right, back for a little bit more about corollaries of the inscribed angle theorem, basically special cases and pretty simple other consequences. It really has a lot of consequences. It's very cool. Remember, this is the most general setup where I have a random arc on a circle and a totally other random point, and I'm just looking at that arc from this other point, and I get half the angle that I would get as if I looked from the center. Remember, there was one special case where one of these was a diameter, but there's another special case where I'm going to take this guy and I'm going to open the arc up to be a diameter. That's a very natural special case. And notice what happens. Well, we can predict what happens. This is still an arc. This is still an angle. It's a kind of extreme angle. It's a straight angle. It's a 180 degree. It's half of the circle. And guess what? Hey, that's pretty darn close to 90 degrees. So I actually set it up especially. I made this perfectly a diameter. And this is a very common special case. Probably the most important special case to know of the inscribed angle theorem is that if you make any diameter of a circle, and then you take any other point on the circle and make this inscribed triangle, one of whose sides is perfectly a diameter of the circle, then this is always going to be a 90 degree angle. And the converse is true, is that if you circumscribe a circle, if you start with the triangle and you start with it specifically being a right triangle, and then you draw the circumscribed circle, there's one and only one circle that goes through those 3 points, then the hypotenuse of your right triangle will automatically be a diameter. That's not obvious. And it's a corollary of these ideas of the inscribed angle theorem. Ooh, now it's registering the other way as 270, so that's a little confusing. We'll keep it over here. So this is a very good picture to remember that if you inscribe a triangle with one of the sides being a diameter, the opposite side, the opposite angle will be a right angle. So let's just summarize that, and then I want to show you, I've created a new picture here, but I just want to write that down. The inscribed angle corresponding to a diameter, that's one way to say it, is a right angle. Okay, so that's one of the many ways to say that great fact, the special case about diameters and right angles. And now say here's a problem, and we're basically going to invent a corollary just by doing this problem. I have a quadrilateral, and that's GFEN inscribed in a circle. That's pretty special. It's not some random quadrilateral. All those points happen to lie, those 4 points happen to lie in a circle. That's not just a random thing. It's a special thing. And let me change something a little here. This is a little too special. This happened to be very close to a 90 degree angle. Yeah, because that was the diameter. Okay. Let's say, okay. So this is about 100 degrees. And here's a quadrilateral. It's inscribed in a circle. And I'd like to know what is the angle GNE. In other words, it's the opposite angle to that angle. I'm doing weird stuff. The angle GFE, which is about 100 degrees. Let's round it. Okay, I know that's just disappeared everything. Okay. That's better. Okay. Well, how would we do that? In general, that's not something you can do. You can't just take a random quadrilateral and just say one angle and then just say, oh, I'm going to know the opposite angle. But here I claim you can. Because of the inscribed angle theorem, the measure of the arc from G to N to E, think of yourself as standing at F, that inscribed angle is intercepting this arc from G all the way to N to E. I'm not going to try to put the big arc symbol over it because this computer program doesn't do that. So I'm just going to say GNE. We know what that is. It's just twice this, so that's going to be 200 degrees. Let's do a reality check. 200 degrees, that should be a little more than half of a circle. Yeah, okay, plausible. A bit more than half of a circle. Okay. All right, so that's cool. Now what about N? we want the angle GNE. Well, that's 1/2 of a different arc. That's 1/2 of the measure of the arc that's the other part of the circle, GFE. I'm just not doing well with my parentheses here. Okay. There we go. So it's 1/2 of that. But wait a minute. If this is 200 degrees, this arc over here is 200 degrees out of the circle, I know what's left over. The whole circle is 360 degrees. And so that measure of that arc is 160 degrees. I don't feel like I'm not typing well. Sorry about that. That's 80 degrees. And we got it. This angle is 80 degrees. Let's test it. Let's see if that works. I think this is going to give me the right one. I always forget. Yeah, 80 degrees. Now, of course, and change because this was a little bit different. But in fact, we can even see, wait a minute, there's a simpler relationship. These guys are supplementary. They add to 180. Why is that? It's because they're each 1/2 of a measure of arc, and those arcs add to 360. If I take two quantities that add to 360, and then I look at half of one and half of the other, they're going to add to 180. So in fact, this is a corollary. This is corollary 3 on page 782. We kind of invented it on the fly. The opposite angles of a quadrilateral, let's just write it out, inscribed in a circle, are supplementary. It's one of those ones that you can memorize, but honestly, it really was just using the inscribed angle theorem and noting, you know, one of those facts that's easy to forget, but isn't that really hard, is that there's 360 degrees in a circle. And that when I'm asked to look at this arc GNE, and then also looking at GFE, hey, those are not unrelated at all. They are exactly, they add up to the whole circle, they add up to 360. And so these angles, the actual inscribed angles, turned out to be supplementary. So it's pretty cool.